Hi everyone. So in the last video, we considered sort of the discrete space, continuous time paradigm, and we discussed the initialization rule. We also discussed the transition rules from state to state. We didn't discuss when a transition happens, and that oftentimes depends on models. So what I'd like to do right now is to sort of give a couple of examples of different sort of common models that we use in the natural sciences. And the first one here is the birth process. Now, oftentimes when I talk about the birth process, it leads to some confusion because people normally think of birth process as involving two individuals giving rise to one, sexual reproduction, or maybe one bacteria splitting up in two, and two then splitting up into four, asexual reproduction. So I don't have any of these models in mind when I talk about a birth process. When I talk about a birth process, I'm thinking of starting off with some kind of number of initial members and then having new members added. Maybe this is at some various time points. So you start off with an initial population, maybe 3 members, and then at some time a new member is added. At some later time, a 5th member is added. So when I think about time and my constitutive states, I'm thinking of my constitutive states as starting off from some value, let's call it k, and then increasing by a fixed amount at various points in time. Right? So that's sort of what I have in mind when I talk about the birth process. So not sexual or asexual reproduction. Well, why is this interesting? One thing we may want to learn from the birth process could be, for example, the amount of time that it takes to add a new member, especially if those new members are added sort of at random times. Maybe they're the time at which a new member is added, or in other words, a jump time, is drawn perhaps from an exponential distribution. And my goal from a couple of draws of that exponential could be to learn the scale or the rate constant. So let's say a couple of things about the birth process. So the state Sn here defines the population of your group just before the mth birth event. So in some sense, we're going to say that sigma m is equal to m minus 1. M here could be 1, 2, and so forth. So if m is equal to 1, before the birth event, the population, or the sigma, is equal to 0. Before the second birth event, the population is equal to 1, and so on and so forth. I'm also going to define here what sk is. It's going to be k, or sn is. It's going to be k, the initial population, plus n minus 1. Right? So before a particular birth event, let's say 1, the first birth event, my population is k, so Sn is equal to k. After the second birth event, then I have k plus 1. Right? So let's go ahead and define my initialization rule, then talk about my transition rule, look at what my transition probability matrix is, and then come up with a model for when these jump times should occur, right? And then talk about what parameters are there to learn if we observe a birth process. I've already sort of alluded to it. The one interesting parameter will be the scale parameter, or the rate parameter. But we'll see why maybe it's of less interest to learn the elements of the transition probability matrix. So what's my initialization rule? So S1 is drawn from a categorical distribution. And, I can have very many constitutive states in this case. It depends on how many birth events I monitor. Now, typically speaking, if I know that I'm starting off with 0 members or 0 population, or I know if I'm starting off with 1 member or population 1, then maybe my row looks like this. Or if I start off with 1 member, maybe my row looks something like this. Those are examples of row. So in this case, S1 is not really stochastic or random anymore because I know exactly how many I'm starting from. So I'm always sampling my initial state from that category. So maybe this is an example where it's, my initial state is deterministic. It's a little bit less interesting. And then I have my transition rule. So that's going to be Sn plus 1 conditioned on the realization, small sn, itself is sampled from a categorical, 0, 1, 2, pi sub Sn. And pi sub Sn is the probability of transition. Now, let's talk about what the transition from state, 0, 1, all the way to big M would be. We already know that the diagonals of this transition probability matrix are all going to be 0 within this paradigm, because when something happens, that's by definition because I cannot stay in the same state. I'm moving to another state. Now, the question is, can I go from 0 population to population 1? Yes, I can. With what probability? With probability 1, because what I do know is that when a jump happens, I cannot jump within this model from population 0 to population 2, or from population 0 to population 3, and so forth. So all of the elements of this row are 0, except for those coinciding with transition from 0 to 1. What about from 1 to 0, this element here? Well, this is a birth process, not a death process, so you cannot go from population 1 to population 0. So the probability of that is 0. By definition, within this paradigm, you cannot stay within your state, and therefore you can only jump from state 1 to state 2. So we're probably starting to notice a pattern here, is that it's the upper diagonal, so all of these elements here that are all going to be 1s, and everything else in the lower diagonal is going to be a giant 0. So in fact, there's nothing to learn in here. How I transition from state to state is kind of dictated by the form of this problem, and it's a birth process. So if I know what my initial state population is, and I specify that it's a birth process, and therefore the pi takes on this, the transition probability matrix takes on this form, the individual pi's that I add to my categorical here are individual rows of this probability transition matrix, depending on what state I start from. If there's nothing to learn, then we need to turn to the next thing. And the next thing is how the holding times are drawn. So we're going to say that the nth holding time is drawn from an exponential distribution with some rate lambda b. And lambda b is going to be the birth rate. So the birth process is something that we also call the renewal process. And it's worth kind of defining here for just 1 second what a renewal process is. So this is when Hn is sampled from the same distribution independently of the state in which I'm in, right? So your probability of some particular holding time is dictated by an exponential with a rate that doesn't care about the size of your population. So in other words, I have some population, then I stay in this particular state for some holding time h1, then I add a new member, and it's deterministic. I'm not adding 3 members or 4 members or maybe 1 member is dying. In fact, the state that I'm going to is deterministic, which is why my transition probability matrix is also deterministic. and then there's going to be some holding time in this state, and then I will have 3 members, and maybe some holding time in this state, and now there's going to be 4 members. And notice that not all holding times have the same duration, again, because they're being drawn from the exponential distribution. The mode of the exponential distribution, in other words, the highest probability event, is actually very small, it's 0. So you're going to have a couple of short times, and you're maybe going to have some long times in proportion to what the birth rate is. So if the birth rate is very small, then the holding times could indeed be very long, right? So maybe if we look at sort of the population, or let's still call them constitutive states, even in the case of the birth process versus time, is that we wait some time, then we add a new member, then we wait some time, we add a new member, then wait some more time, add a new member, and so forth. Add a new member and so forth. The distance between these, is all the same, in some sense, 1, because I keep on adding 1 member at various points in time. I know this is a little bit messy, but this is supposed to be an arrow 1, and so forth. Well, this was pretty simple because the transition probability matrix was in fact very simple itself. And we can now turn to something a little bit more complicated, but not that much more complicated. It's going to be the death process, and you can already sort of imagine what that's going to be. So in this case, we're going to start off with some initial population, and then that population will start decaying. It's going to be a little bit more complicated simply because of the following. Suppose that I start off with k initial members, and again, these are my constitutive states. And each member has some probability of being removed from the group. And maybe the waiting time for each one of them is exponential. So what's going to happen here? What's going to happen is that initially I may have very many members, and each one of them has some probability of being removed from the group. So the more members I have initially, the more are disappearing. So a lot of events are happening, but then events start slowing down, and you end up with, a process that looks more like this. So what's going on? So for example, if I say that you have, some probability of passing away, and that you have, 10 billion people on the planet, then initially, and assume that there's no birth process, then initially you're going to have a lot of deaths, right? Because all of these events are all competing against one another. But eventually it'll start slowing down as your population decreases. Because yes, those events are competing against each other, but you're not starting off with such a large population. So maybe a better way to draw this region here is simply to say that if I were to zoom in, then we see very many events happening right away where a lot of population is dropping, but eventually it's starting to slow down, right? This is not an example of a renewal process because in this case, the rate of death depends on the state in which you're in. So we would call this a Markov renewal process. It has a different name. And this is where only holding times with holding states in the same constitutive state are identically distributed. So now, in a birth process, we just had a lambda b. That was our birth rate. But what's going to happen for the death process is that our rate will depend on Sn. So the rate depends on Sn. So the particular model for it is as follows, that lambda sub Sn is equal to Sn times lambda d. Lambda d now is the death rate, or the sort of the death rate or extinction rate or something like that for each member. Now, if you look at the appendix of the textbook, we actually derive the fact that if any individual member has some rate lambda d before undergoing a jump to another state, in this case it's sort of being removed from the group, then if I consider very many members, then the rate is going to be Sn times lambda d. We derive that in the appendix, and I encourage you to take a look. So at this point, if you were to look at data, and again, I'm going to draw what the death process looks like. That looks something like this, where very many events are happening initially, and then stuff starts slowing down. It isn't so obvious how to go about estimating the death rate. So naively you would say, well, maybe it's the average time that I spend in the last couple of states. But remember, those states here depend on how many members you have. So they have to be reweighted according to the members you have. So in order to do this calculation carefully, you would have to write down a likelihood for this entire event, for the data as you have observed it. And only once you've written down a likelihood is it going to become clear how to go about estimating the death rate. Now, a couple more things. The death rate is still trivial in the sense that maybe you know how many members you start off with. So maybe you, and this is a 0, maybe you start off with 100 members or something like that. And it's also a little bit trivial because now the transition probability matrix, again, still will have zeros along the diagonals, but it'll have a 1 in the bottom off diagonal, zeros everywhere else here, and zeros in the upper diagonal. So in other words, you simply cannot undergo, you simply cannot sort of generate new members, and so the entire upper diagonal, or upper triangular diagonal of this matrix here is 0. So there's nothing to learn in pi because it's kind of already a given, and there's nothing to learn in rho because again it's also kind of a given. The birth-death process will now be a lot more interesting because at this point you have a choice as to whether to add a member or to remove a member, and that's going to depend on the relative birth process rate and the death process rate. So birth-death is going to be more interesting, and that's what we now turn to. But before I do that, we'll do it in the next video. Thanks.